In this ICFD++ tutorial, entitled Isothermal Cavitation in a Throttle, we are going to demonstrate the steps to set up and model isothermal cavitation using the new Integral Computational Multiphysics Advanced User Interface, or ICMP AUI. In this example, the setup of a cavitating throttle is demonstrated using two different techniques for modeling cavitation. In the first section, a mixture model approach is used along with a Rayleigh-Plesset-based cavitation model. The second section uses a time-based Riemann solver-based approach, and a lookup table is used to determine the density from the computed pressure. Before starting the example, I will briefly cover the new features and components of the ICFD++ AUI for our first-time users. For a more in-depth understanding of the ICMP AUI features that are common across all Metacom software, you can click on the ICMP AUI demo link that will show up at the side of this video, or by referring to the ICMP AUI section of your ICFD++ documentation. First, the ICFD++ interface is composed of 5 items. The menu bar, where my mouse is currently hovering, allows you to access various tools as well as load and save your input file, etc. The toolbar below this has shortcuts to some commonly used functions and controls. The canvas is where the geometry or solution is displayed. The notebook panel shows the ICFD++ setup steps, and the action panel is where much of the problem setup takes place. Within the notebook panel, ICFD++ shows an action tree or setup wizard, which can guide you step by step through the various parts of the problem setup. There are also one or more information trees. In this case, we can see the groups and boundary families tree and the boundary conditions tree. Each item in the action tree or information tree has corresponding items that show up in the action panel. This is where the user is given specific choices about the problem setup based on information supplied in previous panels. All panels are dockable and resizable, so the user can customize the interface. Next, I'll briefly cover the mouse controls. The mouse is used to control the view of the geometry in the mesh within the canvas. Holding down the left mouse button and moving the mouse up and down or left and right will rotate the geometry about its horizontal or vertical axes. Holding down the middle mouse button and moving the mouse up and down, left or right, allows you to translate the geometry up, down, left or right. Holding down the right mouse button and moving the mouse left or right will rotate the geometry about the axis normal to the screen. Holding down the right mouse button and moving the mouse up or down will zoom the view in or out. Next, I will open up a new AUI and start the case setup from scratch. In Linux, you can launch the AUI by typing mcfd AUI in a command shell. The user interface will open and we will see the first item in the action panel. The first panel prompts us to choose a working directory. In Linux, the default directory location is where you launch the user interface. So next I will press OK to accept the working directory, and at this point we can select yes to both analyze our grid files and read the BC family file. We'll press OK. Next we'll see information about the cell type and cell count and BC selector names, etc. We can press OK, and we can press OK in the cell types and volumes action panel. Next, we see the general problem definition action panel. We will be solving a viscous, turbulent, single species, multi-phase, non-reacting flow problem. This falls into the category of a general fluids problem, so we'll select this option in the pull-down menu. We'll choose no to use one of the preset problem wizards and press OK. Next, we'll see the CFD problem definition panel, and here we choose the following options. For the fluid type, we're dealing with a multi-phase flow, so we'll choose that. In this case, we'll choose yes for whether or not the fluids are miscible. In this case, they'll be considered to be well mixed within any given cell. The secondary phase will be treated as a mixture with the primary phase. In this case, the primary phase fluid will be a liquid, so we'll select that option. Down below, we'll see an option for whether or not this liquid is compressible. We'll leave that set to no. We'll say yes to the options for a viscous flow and a turbulent flow, and we'll turn off energy transport. In this case, we'll accept the default setting for a steady state simulation and press OK. The next action panel is the additional specifications. In this case, we'll accept all the defaults set to no and press OK. Next, we'll see the equation properties panel. Here we'll choose the two-equation realizable K-epsilon turbulence model. We'll select no to define passive scalars. We'll accept the option to declare one secondary phase, and we'll press OK. Next, we'll see the physics source terms panel. This panel allows us to introduce various types of source term effects. We'll choose no to these options and press OK. Next, we'll see the reference quantities panel. We'll choose to solve this problem in SI units. We also see that the option for solving this problem in dimensional mode is already turned on, and we'll press OK. Next, we'll see the fluid properties panel for the primary phase. Here, we'll highlight the primary phase and press the Edit button. And in this panel, we'll specify the fluid type. You'll see that water is the default fluid type. We'll accept the properties for water and press OK. In this panel, we'll make sure that we set the base pressure to 0, and we'll also change the bulk temperature to 313 Kelvin. We'll select no to enable buoyancy effects, and we won't use any of the advanced settings, so we'll leave those set to no and press OK. Next, we'll see the mixture model secondary phase properties. We can enter the name vapor for the secondary phase. We can leave the density set to constant. We can leave the viscosity also set to constant. We'll enter a viscosity value of 1 e to the negative 5. The density will actually be overwritten by the selection we use in the next panel. We'll select no for allowing a drift velocity. We can select yes for enabling a cavitation model and press OK. Next, we'll see the cavitation model input panel. We can select the Zwart-Gerber-Ballemery cavitation model. The user will notice the various parameters they can enter to describe the cavitation in the left-hand side at the top of this action panel. We will leave most all of these entries in their default state. At the bottom of this panel, we'll select the option to override the vapor density. Here, we will compute the vapor density using saturation conditions. So we'll make sure to input the proper molecular weight for water. We'll choose no to treat the secondary phase as compressible, and select OK at the bottom of this panel. Next, we'll see the initial conditions action tree panel. We'll choose the option to initialize the entire domain. We can press the green plus sign to add an initial condition information set. We need to check the radio button for that initial condition, and we'll enter the following values. For the static pressure, we'll enter 3 e to the 6 pascals. For the U component of velocity, we'll enter 10 meters per second. For the Y and Z components of velocity, we'll enter 0. Down below we'll see the turbulence quantities. We'll leave those in their default state, change those at a later time. We'll keep the vapor volume fraction set to 0.0, which means that initially there's no vapor in the domain, and press OK. Next we'll see the boundary conditions action tree panel. We can see the different boundary conditions in the information tree shown in the notebook panel. We can click on each of these boundary conditions and we'll see that each of these is highlighted. We can zoom in. We can also toggle the 2D display option in the toolbar. So we can start off by dragging the inflow boundary condition to the open category. Under the boundary condition subgroup, we'll choose inflow and outflow. We'll specify the information using primitive variables. We will reuse the information set that was already defined for the initial condition. In this case, we'll highlight that information set and double check that its values are consistent. We'll keep the present turbulence quantities. We'll also keep the vapor fraction set to 0. We won't use velocity ramping, and we'll press OK. You can see that there's a green check mark next to the inflow boundary condition, meaning we've already set up that boundary. So next we'll drag the outflow boundary to the open category. In this case, we'll choose outflow only. For the type of information, we'll choose pressure. In this case, we'll choose a back pressure imposition. Here we'll create a new information set by pressing the green plus sign. We'll highlight the back pressure boundary condition, and we'll set the following values. For the back pressure, we'll enter 3 megapascals, and we'll keep the other options in their default state. Press OK. Next we'll drag the BC named symmetry to the symmetry boundary condition type. Here we will choose the basic symmetry option and press OK. Next we'll drag the BC named wall to the wall category. Here we will choose viscous, wall function, stationary with respect to mesh motion. We won't choose any of these additional options, and we'll press OK. Next we can accept all the boundary condition settings, and we see that each of our boundary conditions has a green check mark, and we can press OK. Next we see the turbulence control action tree panel. Here we can accept all the default settings and press OK. Next we will see the turbulence initialization action tree panel. Here we will need to select the only information set. This corresponds to the initial condition and the main inflow boundary condition. We can right click this information set. We will choose yes at the top of this panel to indicate that we know the turbulence length scale. We won't use a suggestion for the turbulence level. We will enter a turbulence level of 0.03, a turbulence length scale of 0.001 meters, and you will see that the appropriate velocity scale of 10 meters per second is already set. At this point we will press the compute button. We will see the values for K and epsilon that will be applied. We can press OK, and we can press OK to accept these values. This completes the initialization and boundary condition specification of the turbulence quantities. We can press OK. Next, we see a panel prompting us to choose if we want help setting up the numerical options. In this case, we can select Yes for the numerical settings based on physical regimes. In this case, we can select both the Riemann solver and time integration options and press OK. Next, we will see the Riemann solver panel. Here we can accept all the default settings and press OK. Next, we will see the simulation strategy panel. We will choose No for a restart. We can run for 2,000 steps. We can keep the convergence criteria set to 5.0 orders of magnitude. We won't set any of the advanced convergence controls, and we'll press OK. Next, we will see the time integration panel. For the global time step type, we will choose the Auto option. We can keep the first set of defaults in the top of the panel. In this case, we'll reduce the maximum CFL from 50 to 25, since this case involves cavitation. We'll also reduce the coupled solver under relaxation value from 0.5 to 0.33 and press OK. Next, we will see the spatial discretization panel. Here we want to make sure that we're running a second order mode. We'll need to change the dimensionality of the polynomial to 2D axisymmetric. In the advanced control panel, we will turn on the centroidal polynomial type. Press Yes to the pop-up box and set OK. Next, we will see the neutral plot files option panel. Here we can view the default variables that are already selected. These are the variables that will be written to the plotting files. We can select these default variables. In the top pull-down menu, we can also select the mixture model. And here, we can enable volume fraction and press OK. And once again, press OK in the pop-up box. We can accept the defaults for the probe and output options panel by pressing OK. At this point, we're prompted to save the input file. We can do that by pressing OK. So at this point, the first section of this example is ready to run. So we can go to the Tools menu. At the bottom, we see an option to run CFD++. In this case, we'll choose double precision, a single CPU, and then press on the Run button. Here we can see that the case is running and files are being written to our working directory. For more information about post-processing and visualization, you can refer to the results section of this example. And this completes the first section of the isothermal cavitation tutorial. After this run is finished, we can complete the final part of this tutorial by modifying the CFD problem definition panel. The second section uses a time-dependent Riemann solver-based approach via the compressible liquid option, which uses a lookup table that is used to determine the density from the computed pressure. So we go to the CFD problem definition panel, and here we will modify the option that defines how the secondary phase is handled. Instead of the mixture option, we'll choose internal thermal properties. We'll see that this will automatically change the simulation type to a transient simulation. We can keep the remaining settings in this panel and press OK. At this point, we will need to accept some of the existing settings in the subsequent panels by simply pressing OK. So in the Equation Properties panel, we can press OK. Physics source term, we can accept the current condition of that panel. Once again, the reference quantities will be unchanged. We will need to modify the fluid properties panel for the primary phase. So we can highlight the information set for the primary phase fluid properties and press the edit button. Now we see that the primary phase remains water, but now the density is computed using a file-based function of pressure. In this case, we'll use an ASCII fluid data reader. Our file does not contain vapor fractions, so we can set this to no. We'll need to type the correct name for the file. In this case, the file name is density313k.dat. We can enter a minimum density of 0.1 kilogram per meter cubed. This is the minimum density that you'll see in the file. We can use a liquid viscosity law, and we can accept the remaining entries in this panel by pressing OK. At this point, we will need to accept the present settings in a few more panels by simply pressing OK. The initial conditions won't change, so we can press OK. The boundary conditions can be left unchanged. Also in the Help Set Numerics panel. And in the Simulation Strategy panel, we can press OK. Now we'll note in the Time Integration panel that we're running a multi-stage run-kutta time integration scheme, and we're choosing a global time step size that is based on a CFL number of 0.8. So we can press OK. Once again, press OK in the Spatial Discretization panel. In the Neutral Plot Options panel, you can press OK. And the Probing and Output Options panel. At this point, we're prompted to save the input file, so we can press OK. At this point, we prepared the input file to run the second section of this tutorial. So we can go to the Tools menu, Run CFD++. We'll choose to run in double precision on a single CPU. We can press the Run button. Once again, we can see that the solution and plot files are written to our working directory. For information on post-processing, you can refer to the results section of this example.